Welcome to the TOEFL Listening section. In this section, you will listen to an academic lecture and then answer questions about what you heard. You may take notes while you listen. You will have time to review your notes before answering the questions. Listen to part of a lecture in a university class. You will hear the lecture only once, so listen carefully. After the lecture, you will answer some questions about what you heard. Some questions ask about the main ideas and supporting details. Other questions ask you to make inferences or connections between ideas. Answer each question based on what is stated or implied in the lecture.
Good morning, everyone. Today we will examine earthquake prediction methods and the current technologies and limitations that shape this field. I will focus exclusively on methods that attempt to predict the timing, location, or magnitude of earthquakes rather than on rapid alert systems that detect shaking after an event begins. First, I want to distinguish short-term deterministic prediction from probabilistic forecasting. Long-term forecasts provide probabilities over decades, while short-term prediction attempts to specify a narrower window in time and space. Historically, scientists have used seismicity patterns such as foreshock sequences and the seismic gap hypothesis as candidate predictors. The Parkfield experiment in California is a useful case study. Researchers expected a moderate quake around 1988 based on a renewal model, but the anticipated event did not occur until 2004. This case highlighted limitations of relying solely on simple recurrence models. Another well-known example is Haicheng, China, in 1975, where authorities issued a warning after anomalous foreshock activity and unusual animal behavior. Many argue that human intervention and evacuation reduced casualties. But the Haicheng case remains controversial because the signals were not consistently reproducible elsewhere. Turning to instrumentation, modern prediction research uses a network of technologies. Broadband seismometers detect microseismicity, GPS, and InSAR provide measurements of crustal deformation over time and space. Borehole strainmeters and tiltmeters measure very small strain changes in the shallow crust. These datasets feed both statistical algorithms and physics-based models. To be specific, InSAR is particularly valuable for mapping surface deformation over wide areas because satellite interferograms reveal millimeter-scale displacement across a region. GPS provides continuous point measurements that capture transient slow-slip events. Physics-based approaches use rate and state friction laws and numerical models of fault interaction to simulate stress transfer and estimate time-dependent probability. These models can incorporate observed deformation and seismicity, but they remain sensitive to poorly constrained parameters, like fault friction and fluid pressure. Statistical algorithms such as the CN and M8 methods analyze patterns of seismicity to identify increased probability windows. They have produced some retrospective successes, but also many false alarms and missed events. The evaluation of these algorithms emphasizes the need for objective testing and independent verification. More recently, machine learning offers promise by detecting subtle patterns in large datasets. Deep learning applied to continuous seismic records can find repeating earthquakes, tremor, and emergent signals that escape traditional analysis. Yet these methods require extensive labeled data, and their black box nature complicates physical interpretation. There are also claims about non-seismic precursors, such as radon anomalies, electromagnetic changes, and groundwater fluctuations. Some monitoring programs test these channels, but results are inconsistent and often confounded by environmental noise. Radon gas spikes and electromagnetic anomalies are tempting, but they often correlate with non-seismic processes and require careful statistical control before they can be regarded as reliable predictors. A major limitation across all methods is the heterogeneous nature of the crust. Faults differ in geometry, material properties, and stress history. This heterogeneity reduces the transferability of a method that works in one region to another region. Data sparsity is another key constraint. Many regions lack dense instrumentation, so signals are missed or ambiguous. Moreover, continuous high-fidelity monitoring is expensive and requires sustained funding. Ethical and communication challenges compound the technical issues. If a prediction system issues frequent false alarms, it may erode public trust. Conversely, underwarning has obvious consequences. Any operational prediction effort must balance scientific uncertainty with social responsibility. In conclusion, a multidisciplinary approach combining dense instrumentation, InSAR GPS, borehole sensors, statistical algorithms, physics-based models, and machine learning offers the best path forward. Yet we must remain realistic about current limits. Short-term deterministic prediction is still elusive, and most progress is incremental, improving probability estimates and local situational awareness. For our next session, read the Parkfield experiment papers and a recent review on machine learning and seismology, so we can discuss evaluation frameworks and reproducibility.
Listen again to part of the lecture, then answer the question.
Radon gas spikes and electromagnetic anomalies are tempting, but they often correlate with non-seismic processes and require careful statistical control before they can be regarded as reliable predictors.
This concludes the listening section. For more TOEFL practice tests and study materials, visit Spinta.org.